recording. Today we're having Travis, and Travis is going to talk about different models for the Grothendieck polynomials. Thank you for coming.
All right. Thank you very much for having me. And sorry you're going to have to deal with my horrible handwriting here, but I was way too lazy to make a whole bunch of Beamer pictures using TIC-C, so I decided to handwrite this and at least give some impression of a board talk. And as things may go along here, if you have any questions, can't read anything, feel free to ask. And if I have to write in anything more, then at least I can very quickly and easily do that here. So with that being said, I'm going to be giving a talk here, not so much about three models for these things called dual Grothendieck polynomials, but I'm going to be looking at them from three perspectives. And hopefully between two of them, there'll be enough that it'll justify me giving a talk in a seminar titled about solvable lattice models. So, and this is based upon joint work with Kohei Motegi, who may or may not be here right now. But here's the archive link, and he usually, at least before, has been coming to the seminar. So feel free to also ask him questions as well, if he doesn't mind being put on the spot here. If he does, deep apologies to you. Anyways, so what are dual Grothendieck polynomials? Well, what we're going to be looking at is actually a motivation for coming from a geometric problem, which is studying the Grassmannian, which are k-dimensional subspaces of n-dimensional space. And in particular, I'm going to be working over C because everyone likes algebraically closed field of characteristics 0. And studying the geometry is actually kind of difficult. There's different kinds of singularities that can occur. And we want to, doing the geometry natively is just a little tricky. So we want to do a simpler model, and usually understanding the cohomology is kind of the next simplest thing. But we do actually understand the cohomology of the Grassmannian pretty well, but we're still losing a lot of information. And so to get back a little bit more richness to the structure, we go to its K-theory ring, which you could roughly think as being studying the vector bundles over the Grassmannian. And how we're going to study that are with these special things called Schubert varieties. So here, oops, it's just moving. Okay. So here, I'm going to think of GLN over C, and B will be the Borel subgroup of upper triangular matrices. In this case, P will be a 2-block parabolic. So in terms of like block diagonal matrices, it'll look something like this, where one diagonal block will be k by k, and then the other block will be n minus k by n minus k. And then we look at some orbits, and then we take the closure, and these are what Schubert varieties are. But we don't have to worry too much about them, other than the fact that for the Grassmannian, these are kind of a very nice object, because we can use these to construct a basis for the K-theory ring and understand the multiplication through their intersection, at least at the level of cohomology. And there's lots and lots of other special properties about Schubert varieties that I'm not really going to get into, in part because I don't really understand them, because I don't know the geometry so well. But I'm sure there's plenty of people, a number of them probably in the audience here, who know a lot more about this than I do. So in particular for the Grassmannian, well, these are indexed, this W here is an element of the Vial group, which you can think of as being the permutation matrices. In this case, that's the standard choice for B being the upper triangular matrices here. And what makes these permutations special is they have one descent in them. So if you think of a permutation written in one line notation, there's precisely one place where the sequence is decreasing. And what these are in bijection with are partitions that fit inside of a k by n minus k rectangle. And so here is an example, and then a partition is just some bunch of boxes here that's pushed into the upper left-hand corner as much as possible. So what I'm saying is the K-theory ring has a basis that's indexed by partitions that fit inside of this k by n minus k rectangle. So what are these? Well, these are given if we want to represent this K-theory class. Well, doing it at the level of geometry is, well, at least to me, it's extremely hard, and I don't want to do that. Instead, I want to use something that I know very well. And what we can do is we can actually use symmetric functions, where here we have this thing called a Grothendieck polynomial, which will be a given by a Schur function, which is a symmetric function. And then we're going to have higher order terms. So if we wanted to look at the cohomology, well, we get rid of the higher order terms, and then we just multiply things as we would as symmetric functions. And we have to take a small quotient where anytime we just our shape falls outside of this k by n minus k rectangle, we just declare that to be 0. And we do the same thing at the level of Grothendieck polynomials for the K-theory. And so studying the K-theory ring comes down to understanding kind of these Grothendieck polynomials and how they multiply. And there's nice combinatorial formulas for this. For example, these are due to Buch in 2002. And we can represent the Grothendieck polynomials by a 5-vertex model. This is work with by Motegi and Sakai. And since they're now symmetric functions, there's a natural pairing on the ring of symmetric functions called the Hall inner product, where the Schur functions are an orthonormal basis. And so we can take the dual basis with respect to this inner product, and that dual basis is the dual Grothendieck polynomials. So a lot of this, I'm glossing over just because we're not actually interested so much, at least for this talk, in the Grothendieck polynomials and all of these connections. They are very interesting objects, both at the level of combinatorics, geometry, and integrable systems, but I want to focus on the dual Grothendieck polynomials. And just as a minor point that won't be on the slides, but just to say, I'm not actually in the ring of symmetric functions. I'm in a completion because these higher order terms actually, it's an infinite sum for infinitely many variables. Although I can justify calling them polynomials because if I restrict to finitely many variables, then eventually these higher order terms all cancel out or become 0 because the partitions become too tall. But if you want to think about this in terms of infinite number of variables, then you have to go to a completion of the ring of symmetric functions. But that's a technical point. And so how we're going to first attack this is by looking at it from a point of view of combinatorics, which was done by Lamb and Pilavsky in 2007, where they defined a dual Grothendieck polynomial in the same way. And then what they showed is that you can write a dual Grothendieck polynomial as a sum over reverse plane partitions. So a reverse plane partition is we take our partition lambda, so we thought of it as a stacking of boxes, and we can fill those boxes with integers. And when we fill those with integers, we want to impose some conditions on them. So we're going to take positive integers because we have infinitely many variables. But if we want to do finitely many variables, then we say in variables, then we fill this with 1 up to n. And we're going to require that the rows are and columns are weakly increasing. So if you've seen semi-standard Young tableau, I'm weakening the column condition to be weakly increasing rather than strictly increasing. And how I'm going to count my weight, my x to the t here, well, I'm going to count the number of columns that contain I rather than the number of entries if you're used to that. So in this example here, I have 1, 2, 3 columns that contain 1. So I have an x cubed, 2 columns with a 2, and 2 columns with a 3. And then I have this beta parameter here. That's just counting the number of other boxes that didn't contribute to the weight, which are given by these 3 boxes here colored in purple. So, and we just sum over all possible reverse plane partitions. And again, if there's finitely many variables, then there's only finitely many reverse plane partitions, and we get an honest polynomial. Otherwise, we get a formal power series, but it's again in the ring of symmetric functions. So when we've done this, we've just had this extra parameter beta that encodes the degree, but we could actually be a little bit more particular about this, where we want to record the row that the duplication happens. And so this takes that parameter beta and refines it into parameters t1 up to tl. And I've made a choice here. I've chosen to have my the entry that counts in the column as being the bottommost entry, and then the rest of the entries are going to be the duplicates. And it turns out when you do this, it still remains a symmetric function. That's what Galashan, Grinberg, and Liu did. And then you can use the bijection that Lamb and Pilavsky did that takes a reverse plane partition and maps it to a pair of one being a semi-standard Young tableau. So that's reverse plane partitions with, when you look at the beta equals 0 term, which is equivalently columns strictly increase. And then we have this other object called elegant tableau, where what we do is we take the shape mu, which sits inside of the shape lambda, and we forget about those boxes. That gives us the skew shape. And then we fill those remaining entries following the semi-standard Young tableau condition. But we have this extra condition such that the entries in row I are, this should be strictly less than I. like this. And this condition here is called a flagging. And as part of their bijection, you can go through and check that the x parameters is given by the weight of the semi-standard Young tableau, and the t parameters are given by the weight of the elegant tableau. And this uses this bijection called RSK. That it's a slight variant of it, but this RSK insertion is a very common combinatorial tool when working with partitions and Tableau, and where you insert you add new boxes one at a time based upon a certain word. Things bump around, and it's a very nice bijection that preserves a lot of very good properties. But I'm going to refrain myself very, very hard from talking more about that. As much as I also love talking about crystals, I have to at least put them somewhere in my talk. It's just not appearing on the slide. I said crystals, so I can be at least a little satisfied with that. So we have a combinatorial object. And since this is a solvable lattice models seminar, I should start talking about lattice models. And one way that we can do this is we have the reverse plane partitions. You can build a lattice model for them, but you have to, it doesn't follow the usual 5 vertex, 6 vertex fermionic models. And that's because for these models, you need to have interlacing partitions, which turns out to be the semi-standard condition. You can get around this, but I'm not going to talk about that today. Instead, I'm going to attack this from a different direction, where I'm going to look at my two tableau. And when I look at the elegant tableau, well, it's basically taking that shape mu. So here, the shape mu would be 4, 2, 1. And our shape lambda is 4, 3, 3, like this. And so the skew shape of lambda mod mu are these 3 boxes out here. And I can simply attach them to the semi-standard Young tableau and build a bigger semi-standard Young tableau. But now I'm going to have 2 alphabets, one for x and one for t. And there's still that flagging condition out there, but it's only in terms of the t variables. But still, I can write this as a sum over semi-standard Young tableau with the flagging condition. And we combinatorialists, being the we here, kind of understand how to transform this into a family of non-intersecting lattice paths. This is what's called the Lindstrom-Gesell-Viennot lemma, and it's standard proof in combinatorics to write a Schur function as a determinant of elementary symmetric functions, which is called the Jacobi-Trudi formula. And the Lindstrom-Gesell-Viennot lemma allows us to write this as the non-intersecting lattice paths, this determinant. And so we can, and then there's also a standard bijection where, say, the first path corresponds to the first row, where each entry I is a flat step in the ith row. So here I have 3 flat steps in the first row and 1 flat step in the second row. And then, or sorry, in the, well, second horizontal line, maybe I should say, because I'm doing everything in the first row. For the second row, I have the second path here. And so I have the 2, the 3, and then the T1. And finally, I have the 3 and the 2 T2s for this third row here. And so what I've done is I've taken the semi-standard Young tableau that I'm summing over, and the flagging condition is what gives me kind of these points here, as well as the shape lambda. And the starting points are all bunched down here in the corner. And you just draw all such paths that go up and to the right, and there's a nice bijection between the two. So with all of that, what we have is that in finitely many variables, a dual Grothendieck polynomial is just a sum over these lattice paths. And using this, we can write it 2 ways. The first is using the elementary symmetric functions, and the other way is using the homogeneous. And I guess actually, I misspoke slightly earlier. I should have said homogeneous instead of elementary, because how you get from point A to point B here, if you just had a single path, it's a binomial coefficient, and because you can have repetitions along the horizontal steps, it's a homogeneous symmetric function. And so, yeah, the Lindstrom-Gessel-Viennot lemma is what gives us this condition here. And it's really just a slight modification of because it's a flagged, this could be considered a flagged Schur function. And maybe I should attribute this particular thing to Michelle Vox, where at least I believe her paper in the early 80s, I think, was where she did a Lindstrom-Gessel-Viennot for flagged Schur, which that's all I'm saying a dual Grothendieck polynomial is. It's a flagged Schur function with some of your variables carrying special meaning. But this is a solvable lattice model seminar, so I can't talk about combinatorics the entire time. And what I'm going to do is I'm just going to say, well, these non-intersecting lattice paths sure look an awful lot like a lattice model. And in fact, they are. This is one of the more classic lattice models, at least so I've been led to believe by people who are actual experts in this area. And you can just check that around each crossing in my square grid, I get one of these 5 conditions here. I get that, well, nothing happens. I get a vertical line, I get a horizontal line, or I get something that goes up and to the right, or comes in and turns left and goes out up. And then, well, each of the flat, but here I'm not actually recording weights around each of these crosses, but instead in the middle of the flat steps. So I have a choice. I can either take that flat step and have the weight count to the left, or I can have it count to the right. And well, each flat step through here, well, there's a flat step over here and a flat step over here. So this vertex doesn't change no matter which way you do it, but you have a choice over here. And so you can either start them, if this is Z, then you've started it to the left. If this is Z, then everything goes to the right with how you count them, but it ends up counting the same thing. And it turns out that this, in either case, it is a solvable lattice model with a nice R matrix and everything that you're used to.
I have a brief question, if you don't mind. So
Please.
the usual five vertex matrices that I at least am used to are the ones where one of the weights C1 or C2 are the ones that are not permitted, but the intersections are permitted. But here we have another one. Is there some sort of duality between them, or it is just two different ways? These correspond to non-intersecting things, and the other correspond to basically the Weyl group.
So what's happening here is, like, the model you're having is kind of like a slanted version of this one. So yeah, instead, you know, like in your version, a straight line would be like a diagonal here. Well, diagonal means goes up and over, up and over, up and over like this. And if you want to correct that, well, you would push back everything to a straight line, and this removes the intersections, that kind of touching point like this. And that's the kind of equivalence of this.
Okay, thank you so much.
Are there any other questions?
I have a question, but maybe I should ask it later. So your corollary is some version of the Jacobi-Trudy identities, right?
Yes.
So would there be a variation of this proof that would give you the usual Jacobi-Trudy identities?
It's actually no different than the Jacobi-Trudy. If you specialize all of the t's to 0, then you get precisely the Jacobi-Trudy.
So your answer is yes.
Yep, for straight shapes, as Dari pointed out.
Okay, so I didn't know how to do that, but so maybe.
Yeah, so if all of the t's are 0, then what happens is that you can't have any flat steps up in this part. And so everything then above this dotted line becomes a fixed vertical, and then they just drop down to here as being your endpoints, and you can forget about everything up here. And this is the classical Jacobi-Trudy proof.
Okay. So where does the determinant come from?
From the Lindstrom-Gesell-Viennot lemma.
Aha.
So yeah, because the LGV lemma says that if you're given a edge-weighted directed graph, a bunch of start points and a bunch of endpoints, then then you look at the determinant of the where the ith entry is from the ith starting point to the jth ending point, where you look at all possible weighted paths, and then it allows you to get rid of all paths that intersect, and up to a sign where the sign comes from permuting the starting vertices and the ending vertices. And for this case, well, there's no way that I could have, say, this point here end up at this point here without a crossing. So I only have the identity permutation, which has a sign of +1. And so I just am counting non-intersecting lattice paths starting from these points down here to these points up here.
Thank you.
Any other questions? All right. And so we'll see this choice actually coming up in just a second here and why we need that. But what we're going to do now is we're going to take some ideas from solvable lattice models, mainly, well, when we're given a model, we want to cut it up into different pieces or paste those pieces together. And well, we have this kind of jagged, staggering flag condition, but so putting them together, at least naively, doesn't quite work. But turns out we actually don't have to go very far off. So for solvable lattice models proof of the Cauchy identity, you stack the Schur with Schur, and you allow your lambda to go over all partitions inside of an m by L rectangle. But here we have this extra t part, but because of the flagging condition, that tells us that, well, as we go along from left to right in the t range, well, how we make the cut for that jagged edge is, well, we have our first path and we find the first place it intersects up here with this top dotted line. And then we drop that down, and now we have a second line here. We find the point where the second path intersects, and then we drop it down to this third one, and so on and so on. And so this dividing line here gives us a way to break this bottom half into a Grothendieck, and then this top half into a Grothendieck. But this top half is actually using the opposite choice here because of the rotation, that 180-degree rotation. But because we have that choice, well, we know that it's still equal to a dual Grothendieck. And so when we look at this model here, this is just the Schur function for an m by L rectangle in 3 sets of variables: the x's, the t's, and the y's. And so, and that gives us this identity, this Cauchy type identity, where this Schur function in 3 variables is a sum over a product of 2 dual Grothendieck's, one for the shape lambda and one for its complement shape, lambda dagger. And the first one is in the first set of variables x, and the second one is in the second variables y. And the t parameters, we just have to write them backwards because, well, we're looking at this kind of upside down. And then we can play the exact same game where we forget about the y variables, and we get this what's known as a Littlewood identity, where again we take our endpoints and kind of shove them over here, and when we can take that exact same idea of cutting it, and then, well, we have these extra flat steps that are left over, and that's what gives us our this extra factor of t out here. But again, we're summing over all dual Grothendieck polynomials that fit inside of an m by L rectangle. And then if you wanted to, you can also generalize this to a more arbitrary lambda, and well, maybe I should say arbitrary nu here, and then lambda would have to fit inside of the of new, but you could play the same game. And then this also allows us to define a branching rule where we go from, we take, say, the last variable in the x's, and then we want to bring it around into the t's. And we just play this, we take that normal cutting line, and then we drop it one step below, and we see what kind of differences that can come from this single line here. And that's what this is counting, these extra coefficients up here. So we get a lot of identities more or less for free by using these techniques from solvable lattice models. And now, so a lot of what I've done, well, you can think of it from either perspective, from the combinatorial perspective as non-intersecting lattice paths, or from the solvable lattice models side. But I've not, in some sense, maybe this is very unsatisfying for people here because I've not used the solvability at all. I've not done anything that you couldn't do with the combinatorics. So to actually make this maybe a little more interesting, well, because of the non-intersecting condition, everything that occurs in this triangle is completely fixed. And as what Slava was saying earlier, there's this maybe more classical 5-vertex model that things touch. That is, well, I want to now slant everything. And that's what the Motegi-Sakai model is when you set that extra parameter, which I will call eta here, to 0. And this is a very classical 5-vertex model that gives Schur functions as the partition function. And I can now just reintroduce that parameter here because it's the same vertex model at eta equals 0. And so I can build new symmetric functions where in the for the dual Grothendieck's, I sum over all elegant tableau, and then I get Schur functions coming out because, well, that's what this part is. It's a Schur function. And then I get the extra bit that I'm summing over here. And now from the Motegi-Sakai model, instead of Schur functions, I get Grothendieck polynomials. Well, I should maybe call them symmetric Grothendieck polynomials to avoid confusion with other Grothendieck polynomials. But and then I get some t's that, and then I sum over now set valued elegant tableau as well, where the semi-standard, well, they're now filled with sets instead of positive integers, but they're finite, non-empty, finite sets, where my semi-standard condition is I take the maximum of this entry A, and that has to be less than or equal to the minimum of the entry to its right, and strictly less than the minimum of the entry to its bottom. And another way you can think about this is a set valued elegant tableau is an elegant tableau, or if you take any entry from any of the sets, you still get an elegant tableau back again. That's another way you can think of the set valued condition. But I don't know too much about what these symmetric functions actually are, but maybe they'll be of interest and someone can connect them with an interesting object. Maybe someone knows an object out there that, you know, both increases and decreases like this in some natural and important way. But I'm going to look at what happens when I specialize eta to 0, because in that case, we know that we have a nice determinant formula for this lattice model coming from a lot of classical analysis, but now we actually are truly using the power of the lattice model to get this determinant formula for the sum over Grothendieck polynomials that fit inside of an m by L rectangle, which I will call a Cauchy-Littlewood identity just to distinguish it from the Cauchy identity and the Littlewood identity, but this appears, this has been called both of them, but at least, yeah, I can write the sum over Grothendieck polynomials as this particular determinant here. So yeah, I can actually get some honest lattice models stuff that I can't do at the level of combinatorics by making this deformation here. And so with that, we're going to switch to the third perspective. And unfortunately here, I don't really have a good lattice model interpretation for this. And maybe someone in the audience will be able to do something about that. So this will be a more combinatorial type description here. Well, combinatorial and algebraic, but it's an interesting connection that since probability theory keeps coming up in this seminar, I mean, granted, it's probabilistic lattice models, but yeah, hopefully someone will be able to find a nice connection here. So the probability or the stochastic process I want to look at is a very old one called the totally symmetric asymmetric simple exclusion process, better known as TASEP. And I'm going to be working on the infinite line and starting with the step initial condition, which means that, well, at the initial point here, I'll have 2, 3, 5. I have my starting condition is there's some place where I cut where everything to the right is empty and everything to the left is filled with particles, which math physicists will sometimes call the Dirac sea. And how this model works is, well, each particle independently can jump to its right with probability Q if there's no particle immediately to its right. And so here's a particular state in this model, and these are the particles that can move to the right, and they will do it with probability Q. This is a discrete version of this stochastic process. And what we want to do now is we want to record the time it takes for the nth particle counted from the right from the step initial condition to move L steps. And we can reformulate this as a random matrix problem. And this last passage, percolation, you could think of as being a generalization of this, where I'm going to take a random matrix where the entries of this matrix are going to be given by random variables that is going to have a geometric distribution. So what that means is it will be equal to a non-negative integer, k, and it'll be equal to k with probability 1 minus ti times xj times ti xj to the kth power. And here ti and xj will be real numbers between 0 and 1. And I just build out the ij entry like this, and we can make it into an infinite matrix if we want. Index starting from 1, 1 out to infinity. But what we're interested in is what's called the last passage time, which is we look at all paths from 1, 1 to say the point L comma n, and we sum over all of those random entries, and the paths that we're allowed to take either move, increase the column index or the row index. And so they just kind of, in terms of like the usual way we would write matrices, well, they either move right or down until we get to our finish point. And so if we take xi equals tj equals the square root of q, we get the connection back to TASEP, where the time that we actually need for the nth particle to move L steps is given by this value gln plus L plus n minus 1. And that gives us this connection to TASEP. But this random matrix, though, if we want to write the joint distribution, which I will call GI, if we fix an L and we go from I down to 1 in this order, this will be weakly decreasing because every row we add has to be strictly larger in value because we're summing over all possible paths. So I can write these GIs as a partition. And what I'm going to do now is I'm going to write a dual Grothendieck polynomial up to this leading factor here, which is just coming from this factor here that's there in all of the variables. And the transition probability from gi equals lambda to gj equals mu is given by a skew dual Grothendieck polynomial. So the definition I gave was originally for straight shapes, but there's nothing that prevents you from tweaking that definition to use a skew shape. And so I just take it as a skew shape. And how we want to prove this is we're going to just look at the single variable case and do a branching rule, which is very integrable systems, lattice model, single row. And that allows you to, at least when all of the t's are equal to beta, you can do this without maybe too much trouble if you just, as I said at the beginning, change your auxiliary spaces, the horizontal lines, let's say, to be bosonic rather than fermionic. So you can build out a branching rule and you can write it explicitly in terms of the partitions lambda and mu, like this. And then you look at this and you realize, oh, this is also just the combinatorial rule for taking all of the entries in the reverse plane partition and basically getting rid of them. And that's the branching from lambda down to mu for that particular shape. So you get this very explicit way of writing it. And once you realize that they're the same, you can then get arbitrary number of variables by just doing this over and over again for x1, well, xn down to x1. And that is what gives you this identity here, which I guess I should kind of more or less claim that this is a complete proof. And using this and a lot of algebraic manipulations following what Johansson did for the case when all of the t's equal x's equal square root of q, you can build out a determinant formula for the skew dual Grothendieck's in the following way. And it's a little complicated, but it's not too bad. But the proof still is entirely algebraic. And it does take a bit of work to get there. But in some ways, what I'd like to have is a lattice model proof of this, because lattice models should give nice determinant formulas, and you would want to have a nice lattice model interpretation of the refined dual Grothendieck's as well. But that is a, I'm not quite sure how to do this, in part because you have these infinite sums that appear. Now, of course, in any particular I and j, each of these entries ends up being finite because, well, you're subtracting m, and each of the preceding values will always be finite as well. So, and then it's, of course, finite matrices too. I should also say that the approach that Motegi and I did is really based upon these algebraic manipulations. Jung-Soo Kim independently also proved these by using plethistic methods, which is a kind of combinatorial, somewhat representation theoretic sort of manipulations in order to get these determinant formulas as well. But again, it's still kind of algebraic manipulations, not really a lattice model manipulation. But still would like that kind of lattice model type approach to getting the dual Grothendieck's. I have some ideas about how to refine the parameters and write out a colored lattice model. I just haven't had time to really sit down and try and develop it. And but once armed with this, well, getting these Jacobi-Trudy determinant type formulas, I'm not sure how to quite go from that. And this would be something I want to do in the future. I'd also want to understand how these eta-deformed versions of dual Grothendieck polynomials, what they mean, explore some of their properties as symmetric functions. What does the eta parameter mean in terms of the probability theory? And kind of what other, is there a nice, well, I guess in some sense we have this lattice model interpretation, but what's the branching rule and kind of some of these other like skew versions, what would they mean? Because the lattice model I presented initially from the non-intersecting lattice paths is not well behaved with respect to looking at skew shapes. Something else I'd like to look at and figure out would be, what do the refined parameters mean in terms of the geometry? So this beta parameter is natural because it shows up in this thing called connective K-theory. And that's kind of a, a geometric sort of explanation of the T's in some sense, but and I know very, very little about the algebra behind connective K-theory versus normal K-theory, but apparently this is a natural thing. I don't, and my understanding is looking at a refined version of connective K-theory is not something that's possible, but maybe something special happens for the growth in the case of the Grassmannian. I don't know. And Motegi and I also have this integral way to compute a straight shape Grothendieck that's given by this kind of interesting looking formula here. It's very similar to the integral representation of the Schur function for a straight shape. We can actually do a skew shape, but then it's a determinant of integrals, and you can almost certainly get a similar such formula for the skew shapes as well. But be nice to know if this integral kind of shows up in other places, and as well as like, okay, what happens if I change the integrals, these contour integrals, to maybe some kind of Q integral? Because I remember reading somewhere that you can get, I think, Hall-Littlewood's by looking at Q integrals, or maybe it's maybe even McDonald polynomials is like Q integrals of a deformed version of Schur functions, and maybe there's something interesting for doing Q integrals here rather than normal integrals as well. So that is basically everything I wanted to say. So yeah, are there any questions?
Yeah, thank you so much, Travis. Yeah, are there any questions? Let me stop recording.